Okay, so sorry I had to pause that last or stop that last video, but I was recording after school in a room and I was hoping nobody would walk in, and one of the maintenance people had to come in and start working on something in the room and they were going to make a lot of noise. So I had to stop the video and move to a different location because this stupid program doesn't pause. It has to just stop. So, okay, picking up where we left off. All right. So um, this is the information for one of Anna's rolls. We want 5 rolls because 5 rolls makes one game. So you have to really figure out, is this 5 times or is it them added up 5 of them? Okay, that probably didn't make any sense. Let's think about it one more time. I got interrupted again. Someone else came in again. Okay, if you multiply by 5, then that would be saying that each roll is identical. And that's just not realistic. So we're not multiplying by 5. We have 5 separate rolls, so we need to be adding them up, 5 of them. Now, do you remember when we did the delicious dogs, we talked about how 2D did not equal D plus D? Because 2D was 2 of the same size dogs mashed on, but D plus D was 2 randomly selected hot dogs. They might have been different sizes. That's the idea here. 5A is not the same as A plus A plus A plus A plus A. Those are not the same. 5A would be 5 identical rolls, and that's just not feasible when you're rolling, what is a skee ball or whatever. So our scenario is 5 separate rolls, okay? And that is something that is hard to comprehend and hard to wrap your head around because you are so used to algebra where these are the same. And they're not when we're talking about random variables. So what I'm trying to get at is, for a game consists of 5 separate rolls. And if we're going to find the average for a game, we have to do 5 separate rolls. So we would have to do, adding up this 23.8 average plus 23.8 plus 23.8 plus 23.8 plus 23.8. And again, writing on this board is not easy to do, so sorry my handwriting is so bad. Adding all that up, you get 119. That would be her average, expected average number of points per game. Okay? Whew. Now, standard deviation. We cannot add up the standard deviations. We've talked about that a bunch. You cannot add the standard deviations, but you can add the variances. So I can get the variances of 5 rolls. Okay, so I would take, now the variance is the standard deviation squared. So the variance would be 12.63 squared. Okay, so I have 12.63 squared plus another 12.63 squared. That would be for the second roll. Here's the third roll. Here's the fourth roll. And then the fifth roll. Okay, now again, that was the variance. I need the standard deviation. The standard deviation would be the square root of, oh my gosh, my writing is so bad. The square root of all of this stuff. 12.63 squared plus 12.63 squared plus. You get the idea. You could probably write a lot faster than me. Okay, typing all that in your calculator, you get 28.24. Okay, that is your standard deviation for one game. Okay? Whew. So this is the mean for one game. This is the standard deviation for one game. Okay. Now it's asking, what is the probability that Anna rolls a game with a total higher than 150? And we're assuming that a game is approximately normal. Oh man, anytime you see this approximately normal business, you gotta think z-score. Okay? And look, we have the mean for a game and we have the standard deviation for a game. Remember how your z-score formula involves subtracting the mean and dividing by the standard deviation? Okay? We are trying to find the probability, P, that Anna rolls a game with a total higher than 150. So we're looking for X being greater than 150. Okay, use your z-score formula. So we're going to do 150 minus the mean for a game, which is 119, divided by the standard deviation for a game, which is 28.24. Okay, so when you type that in, your z-score is 1.10. Now go back over here and make sure your notation is nice and pretty. So the probability of her game total being higher than 150 is the same thing as the probability of her z-score being greater than 1.10. Okay, now remember this is a greater than problem, so we have to do 1 minus. Look up 1.10 on your chart. When you look up 1.10 on your chart, you get 0.8643. So you have to do 1 minus that, and you get 0.1357. Okay, so the probability that Anna rolls a game with a total higher than 150 is 13.57%. Pretty low chance that she's going to roll a total higher than 150. I mean, look at her expected average. It's 119. 150 is quite a bit higher than that. Okay. So this is a mixture of both sections now. This was 6.2 work, but now when you're talking about probability and you're talking about approximately normal, that's the z-score stuff that we did in 6.1. It all is coming together, okay? It's kind of intense at first. The more you do, the better you're going to get. Okay. All right, now, bear with me because this is the second to last problem we're going to do, and it's pretty involved, so you might need to pause it and stuff like that. Okay, Anna's friend Winnie also plays skee ball. For one game, she has a mean of 140 and a standard deviation of 31.5. Both of these are approximately normal random variables. What's the probability that Anna has a higher score than Winnie? Okay, now remember, on the last page, we had 119 for our mean for a game, and we had 28.24 for our standard deviation for a game. Remember, that was Anna. Okay, Winnie now has, let's let's do W for Winnie's mean. Her mean is 140, and her standard deviation is 31.5. Okay, now we are trying to find the probability that Anna has a higher score than Winnie. If I'm going to write that out, it would be saying Anna, oh man, you know what? I really want to change this to an A for Anna, but I'm going to leave it as a G. Okay, so we want Anna having a higher score than Winnie. So G is going to be higher than W. G would have to be greater than W. Anna's game is greater than Winnie's game. Okay, now as far as random variable stuff goes, we talked about adding and subtracting and multiplying and that sort of stuff. So we need to kind of rewrite this so that it kind of fits our formulas and our rules. So to be clever, I'm going to subtract W over to the left side. So if I subtract W over to the left side, then that would be greater than 0. Now, do you see how we've got two random variables that we're subtracting? So we need to find the new mean for when we're subtracting G minus W. And we need to find the new standard deviation for when we're subtracting G minus W. Because we're finding a probability that's approximately normal, we're going to need to do z-score work. Before we can do the z-score work, we need this information. So we're going to use our formulas. The idea that we're subtracting random variables, we can just subtract the two means. So I can take my mean for Anna and I can subtract the mean for Winnie. Okay, and I'm going to get my new mean of negative 21. That's the mean I'm going to use when I do my z-score. All right, now for the standard deviation. Remember that when you are subtracting random variables, you still add the variances. Okay, so let's deal with the variance first. We are going to add the variances. That was that weird rule that even though you're subtracting, you still add the variances. And then in order to get the standard deviation, I have to take the square root of all that stuff. Okay, so I'm going to take the square root of Anna's standard deviation squared, so that would be 28.24 squared, plus Winnie's standard deviation squared, 31.5 squared. And again, a lot of people just want to add up those two standard deviations, but you cannot do that. The square root does not cancel off those squares. So be very careful of that, okay? So typing that in your calculator, okay, I need a calculator. So we need to do the square root of 28.24 squared plus 31.5 squared, and we're going to get 42.31. So that's the standard deviation I'm going to use for my z-score. Okay, now for the z-score, remember our formula looks like this. What's the value of x? The value of x is 0, which, normally this isn't a 0. Normally this is some number, but in this case it's a 0. So we're going to do 0 minus our new mean of negative 21 divided by our new standard deviation of 42.31. When I do that, I get a z-score of 0.50. Okay, so continuing on with my probability statement, this will equal the probability that our z-score is greater than 0.50. Since it's a greater than, we have to do 1 minus. Look up 0.50 on your chart, and you should see 0.6915. And then when you subtract that from 1, you get 0.3085, which would correspond to 30.85%. So we were finding the probability that Anna has a higher score than Winnie. So 30.85% is the probability that Anna has a higher score than Winnie. Okay. See if I can type in here. Hang on a minute. Okay. Now, I realize that that was a pretty difficult problem. We did a lot of stuff there. When I get back on Monday, we're going to do another example of this. But it's just good to have it in your notes so that you can refer back to it, because you will see it again. And this is something that you do need to know, because there's going to be something like it on the test. So while it might be hard right now, hopefully next week we'll get it cleared up. Okay? Let's see. I think we'll stop there. And now you can have the rest of the period, whatever's left, to work on homework number 3. Okay? All right, have a good weekend, and I'll see you on Monday. Bye.